So today we're going to look at section 1.5, which is on transformations, which the idea of a transformation is when you take a picture or a graph and you slide it up and down, slide it left and right, or you can stretch it up and down and stretch it left and right. Okay, those are all transformations. Throughout the year, we're going to look at transformations on different functions. Today, we're going to look at them with quadratics. So remember, in general, a quadratic has the form ax squared plus bx plus c. And a is always in front of the x squared, the b is in front of the x, and the c is at the end. The a, the b, and the c can be any numbers you want, except a can't be 0. What would happen if you plugged in a 0 for the a? What would that do to my equation? Anyone think they see what would happen? If you plugged in 0 for a. Yeah.
Well, if you did the quadratic formula, it would result in 0, but it also could turn into a y equals mx plus b.
Yeah, it would turn basically a quadratic into a y equals mx plus b, which is a linear, because if you fill in 0 for a, you're going to wipe out the x squared. It's gone. If you don't have a power of 2, you don't have a quadratic anymore. Okay. So the a can't be 0. So let's graph the simplest quadratic, y equals x squared. Just type it in and see what it looks like. So type that in. If anything else is in there, you can clear it out. I would do zoom 6 just to set the window. And we get that shape. Okay, so it's kind of like a U shape. Does anybody know what the name of that shape really is? It's not a U shape. Remember? Yeah.
A parabola.
Yeah, it's a parabola. And do you remember what you call the point at the very bottom? Yep.
Vertex.
Vertex. Yep. Perfect. So I'll mention that in a second, but that's the shape. It's a parabola, and the point at the very bottom is a vertex. Now, let's see what happens if instead of graphing x squared, we graph in parentheses negative x squared. Okay, so I want you to watch what happens to the graph as we do it. So there's the original. Now watch the new one in red. And it's all done. How does the graph of the red one compare to the blue one that I just had on the screen? Have a guess? Yeah?
It's the exact same.
Yeah, it is the same. This negative did do something. It did what we call a reflection, but you can't tell that it reflected it because it took this graph. And if I do the reflection like on the smartboard, you'll be able to tell because all the words are going to look backwards, but the picture is going to look exactly the same. Okay, there's no difference in the picture. So we reflected it over the y-axis. Does anybody know what you call the y-axis? It goes right down the middle of the parabola. And when you flip it, it looks exactly the same.
Axis of symmetry.
Yep, it's called our axis of symmetry. So actually, that's what we say right here. So the y-axis is what we call a line of symmetry. And a parabola is not a good graph for me to try to show you the reflection because it ends up looking the same. The low point on this parabola, that's called the vertex. In this case, what's the coordinate of the vertex?
0, 0.
Yep, the vertex is at 0, 0. Now, the vertex doesn't always have to be the lowest point. If you take the parabola and you flip it over, The vertex could be the highest point. Yeah. Yeah, are you meeting for today? No, you're coming back. Okay. Yeah. Okay. So, any question on what the vertex is? All right. So let's look at what happens when we change just one thing. All I want to do is change the number that's in front of x squared and see what the effect is. So I'm going to try typing in 1/3 x squared. And the way you can type that in is like this. It's one way to do it. 1/3 x squared. And I'm going to type in 2x squared. Okay. I'm going to hit graph. So you're going to see the original again in blue. Now the red is going to be the 1/3 x squared. And then the black, I think it's going to be black. It's going to be the 2x squared. What's happening when you change the number in front of x squared? What's it doing to my graph? Yeah. Yeah, it's we either talk about it stretching or compressing vertically. Think about if all these parabolas were like, like if they were like Play-Doh, right? And they were all glued down at the origin. If you pulled up on the sides of the parabola, it would get taller, it would get skinnier. If you took like the Play-Doh and you squished it down, what would happen? It would spread out sideways, right? It would get wider. So putting a number in front of x squared causes the graph to stretch or compress vertically. The bigger you make the number above 1, the more it will stretch. 1 is the point at which it goes from stretching to compressing. If I did a number like, let's say I put in 6x squared, that's going to stretch it even more than 2x squared. It's going to look even taller and skinnier. Okay, that's the pink one. If I put in a decimal or fraction between 0 or 1, that's going to cause my graph to compress vertically, and that's why it looks wider. So a number between 0 and 1, I could do something like, if I wanted to stretch it a lot, I could do 0.1. The closer that number gets to 0, the more of a vertical compression you're going to get. And it's going to start to make the parabola look very wide. And eventually, if you compress it enough, it might even almost look like it's flat. But if you zoom out, you'll see it. It always has a curve to it. Okay, so any question on what changing the number in front of the x squared does? It's either vertical stretch or vertical compression. Now, I want to still stick with that number, but instead of just changing the number, I also want to change this number and make it a negative. I already showed you what happens if you put a negative on the inside of the function with parentheses. This is like a negative in the front. Does anyone have a guess what this negative in the front is going to do? You're going to see what this one does. The other negative you couldn't see, but this one you will. Yeah, Brady?
It's going to reflect it across the x-axis.
Yeah. Okay, I'm just going to graph one of them to show you. I'm just going to do x squared and negative x squared, not in parentheses this time. Okay, it's just a negative in the front. So you're going to get the original in blue. And then the red one, you're going to see that it's down in quadrants 3 and 4. It flipped over. Okay, so exactly as Braden said, that's a reflection over the x-axis. And it causes the parabola to open down instead of up. What's important to notice when you do transformations like this, what I just circled, that's one transformation. That is a second transformation. There's two different things happening there. That's a vertical stretch. That's a reflection. Okay, they're not together as one thing. Same thing here. This 1/3, that's a vertical compression, and that is a reflection. Okay, so two things happening. In this one, there's only one thing, because you could pretend like there's a 1 in front of the x squared. So it's just reflecting. All right, so what I want to do now is I want to look at example 2, and I want to see if we can figure out, if you had this graph, y equals x squared, how many things you would have to do to it to turn it into that one. Okay, so that's the first step. Anyone think they know how many transformations are happening to turn this into that? Yep.
2.
Yep, there are 2. Let's start with what the 5 does. Okay, let's forget about the negative for now. Okay, what is the 5 going to do? It's going to take this graph that's starting out x squared and
It's going to stretch it out
it's going to stretch it out. Which way?
upwards.
Upward, yeah, vertically. Okay, so the way you describe it is, this is what you write down. Vertical stretch. Okay, but that's not enough. You've got to say vertical stretch by a factor of 5. That tells me it's getting 5 times as tall. So vertical stretch by a factor of 5. Okay, that's the first thing. Now the second thing is that negative. What's that negative going to do? Remember, it's a negative in the front, which we just wrote down. Yep.
It's going to make it reflect over the x-axis.
Yep. So that's reflect over x-axis. Now, when you start doing multiple transformations, there is a certain order you need to write them down in. I kind of guided you through that one, and the order we did is the right order. I'm going to tell you what the order is in a minute. Okay. Questions on that one? All right. So we've played around with the A, right? Let's try something different. Let's see what happens when we add or subtract a number on the end of the function. So we've got y equals x squared, and let's do x squared plus 2. Anyone have a guess what that plus 2 is going to do? Yeah.
It's going to store you at 2 instead of at 0.
Okay, could you describe it in terms of?
It's going to be a parabola. But it's going to start at x. Like it's going to be on the x-axis plus 2.
So you think it's going to move 2 units to the right? Okay. Anyone else have other thoughts? What could happen? Yep.
It'll move 2 units to the
Up. Okay. It's going to be one of those. Let's see what happens. When you add or subtract a number on the end of the function, that takes your graph and it moves it either up or down. Okay. So that plus 2 does move it up 2. So to answer this question, so to get y equals x squared plus 2, we would shift the original up 2. How do you think we would get y equals x squared minus 3? What do you think we'd do to the original graph to get x squared minus 3? Yeah, go ahead, Maggie.
Shift the original down 3.
Yeah, we would shift the original down 3. Okay, these are both examples of what we call translations. in a translation, you are not stretching anything. You're just taking what you have and you're just sliding it somewhere else. That's it. So these are called vertical shifts. Vertical shifts are an example of a rigid motion transformation. Again, rigid motion means no stretching. Slide. And whether you shift up or you shift down, it all depends on the number that's on the end. Okay, so I'm going to give you the two cases. One where you shift up, one where you shift down. But does everybody have that top part? If the number that you put on the end is a positive, +2, +6, +7 1/3, that's going to shift it up. If the number you put on the end is less than 0, if it's a negative, right, like -5, -2/3, okay, any negative number, that's going to shift it down. But what you don't want to say is, like if it was a -2, don't say shift down -2. You can shift up 2 or you can shift down 2. You can't shift down -2. Okay? The amount of the shift is always a positive number. The word that you use in front of it takes care of the negative or the positive. Up, down. Okay. So those are vertical shifts. What other kind of shifts do you think we have? Yeah. Yeah, we have left and right shifts too. So whenever you're adding or subtracting, it is always a shift. Where you do the adding and subtracting controls if it's a vertical shift or a horizontal shift. So the difference with the adding and subtracting this time is it is inside the parentheses. But now my question is, which way do you think, let's look at the first one, the -3. Which way do you think the -3 would move the graph? Yeah? To the right, yes. Sometimes people say to the left because they think negative numbers go to the left, so they think subtracting would go to the left. It's backwards. It doesn't work the way you would expect it. So when I do x -3 and square it, that is going to go to the right 3 units. There's the original. And the red one is the new one, pushed right 3 units. So I can write that down. So to get y equals x -3 squared, shift the original, right 3. So likewise, what do you think x + 2 would do? Which way would that shift it? Yeah, that's going to go to the left. All right, so that one's backwards. So we're going to write that one down. And if you want to make a reference sheet and put that on it, you can. But these are, again, examples of rigid motion transformations. Adding and subtracting this number inside does not stretch or distort anything. It just slides your picture left and right. So here's the 2 things to remember. If the number that you put right here is a positive, if it's bigger than 0, +3, +6, +1.4, positive numbers are going to shift it to the left. If the number that you put where I circled is a negative, -2, -7, -5/3, okay? Any negative number is going to shift it to the right. Again, same deal as before. Don't say that it shifts right -2 units. You can shift right 2 or left 2. You can't shift left or right a negative number. That doesn't make sense. Okay, any questions on that? So I used two letters here. I used H, and this one described left and right movement, and I used K, and that one described up and down movement. What I want to be able to figure out now is when I shift it left, right, up, or down, where does the vertex go? If you don't shift it at all, where is the vertex? If you just draw a regular parabola, y equals x squared. Okay?
0, 0.
It's at 0, 0. If we shift it left and right, it's going to be at a different spot. Where it's going to end up, let me make that bigger so you can read it. I think it kind of... So that is the formula for how you find the new location of your vertex. It's negative h comma k. Why negative? Because the left and right is the opposite of what you would expect. So by putting that negative there, it makes it the opposite. So it's the opposite of the h comma k. Vertex of that. This got messed up a little bit. Let me fix this. So negative hk is where the vertex is. Let's put that there. For that equation, the vertex is at negative hk, and the line of symmetry is x equals, and it's just one of those letters. Think about which one would affect the line of symmetry. Here's a parabola. Here's the line of symmetry. If I take that parabola and move it up, how did the line of symmetry change when I move my parabola up? Yeah, it didn't. How does it change if I move it down? It doesn't change. Moving up and down has nothing to do with the line of symmetry. So the only thing that affects the line of symmetry is moving left and right. That's the equation for your line of symmetry. X equals negative h. Okay, so I'm going to leave those on the board. And let's see if we can figure out where the new vertex and line of symmetry are in this one. And a lot of times, the way I figure it out is I don't even want to have to memorize another formula. I just look at the transformations. What is that plus 2 going to do? It's going to move it which way and how many? Yeah.
To the left 2.
So it's going to go left 2. And what's that minus 3 going to do? Yeah. Down 3. Now think about what would happen to the vertex. If it was at the origin and the vertex went left 2, down 3, what would be the coordinates left 2, down 3 from 0, 0? Yeah,
-2, -3.
-2, -3. Yeah. That's your new vertex. Left 2, down 3. And the line of symmetry, it's always x equals, because it's a vertical line. And it's x equals whatever number we used right there. So in this case, my line of symmetry would be at x equals what number?
-2.
Yep, -2. The line of symmetry is going to move 2 units to the left. Just like everything else in the graph moves 2 units to the left. Moving the line of symmetry down 3, that doesn't do anything. It's a vertical line. Lines go up and down forever. You could move it up 100. That doesn't matter. Yeah. How did we get left? Because it's plus a number inside the parentheses. And anytime you have a number bigger than 0, it moves left. Okay. So now, let's look at this one, and we need to talk about the order. So why does the order matter? Well, think about something like this. If you do this problem the correct way, what do you get for an answer? 2 times 3 plus 5.
11.
How much?
11.
Yeah, if you do it the correct way, you get 11. But if you do 3 plus 5 first, which is the wrong way, 3 plus 5 gives me how much?
7. 8.
8, and then times 2?
16.
16. Well, 11 is not the same as 16. So we have to decide what order we're going to do that in. And it's not that like one order is right and one order is wrong. It's just we decided when we write things in math like that, there's an order we all follow. And as long as we follow the same order, everything works. Green lights you go, red lights you stop. We all follow that, everything's okay. So when we do transformations, there's an order we have to decide that we're all going to agree on and that we're going to follow. And this is the order that we have to do. Okay, the first transformation that we look at are the horizontal shifts. Horizontal shifts are the first thing. If you don't have a horizontal shift, you skip it and you go to the next one. The next transformation you would write down is any vertical stretching or shrinking. Compressing, shrinking, same thing. The next transformation would be any reflections. So we talked about reflecting over the x-axis. That's the one that you can see when you have a parabola. Easier because now it's opening down instead of up. And the last transformation you would write down are any vertical shifts. So for this section, that's all you need to know. That list is slightly incomplete. I don't have horizontal stretches on that list. I also don't have reflections over the y-axis. Those two things would be right in here. We're not going to talk about horizontal stretching or reflecting over the y-axis in this lesson, but eventually we will. Okay, so the big idea is you always do all your horizontal transformations first, then you do all your vertical transformations second. Okay, so let's look at this one. 5x squared plus 4. Does anyone see how many transformations are in that problem? How about Kate? Do you have a guess? Yeah, there's 2. The 5 is going to do something and the 4 is going to do something. All right. Do we have, well, actually, you tell me, which number do we do first? Do we look at the 5 or do we look at the 4 first? Yeah, Natalie? Yep, we're going to look at the 5. That's the number in front of x squared. And that's what we talked about right here. The effect of changing the a. Can anybody tell me what the 5 is going to do? Yeah, go ahead, Matt.
Stretch it.
vertically?
Yep, so that's the first part of what we say. Vertical stretch. But then you have to tell me how much. Does anyone remember the word I used to say that? Vertical stretch. Yeah?
By a factor of 5.
Right. By a factor of 5. Okay, so that's what the 5 is doing. How about the plus 4 at the end? What's the plus 4 going to do? Yeah, Ariel?
It's going to move it left 4.
So it's on the end, so it's going to look more like this one.
It's going to move it.
So which way is that going to move
It's
it?
going to move it up 4.
Up 4. Yep. So the second one is shift up 4. Yep. Okay. Question on those two? Let's try this one. Okay, so same idea. It says describe the transformations. And a good first step is just figuring out how many you have. Okay, so look at what's in that box. Anyone think they know how many transformations you're going to have? Yep, Olivia?
30.
More than 3. Yeah. 4. Yeah, we have every one of them in this one. Yeah. So I think I know why you probably said 3 if you were thinking like the -3 is one thing, but the negative and the 3 are two separate things. All right, since we have all of them, let's go through the list right in order. Which number is my horizontal shift? Yeah, go ahead, Natalie.
-1.
Yep, -1. And which way is that going to shift it? Yep, negative is going to shift to the right. So tell me the direction, and then tell me how much. Shift right. Okay, vertical stretch. Which number here is my vertical stretch? Anthony, now. Yep, Anthony, are you gonna have a guess?
Is it the 3?
The 3, yep. So vertical stretch by a factor of 3. All right. Next thing we have to look at is the negative in front of the 3. Not really much to say other than just what it does. What does the negative do? Yeah, go ahead.
Reflects over the x-axis.
Reflect over the x-axis. Okay, and the only thing we haven't used yet is the plus 4. Gracie, what's the plus 4 going to do?
You're going to do in shift up 4.
Yep, so shift up 4. Okay, any questions on that one? All right, so every problem that I've given to you has been in what we call standard form. And the problems that I give you will always be in standard form. Okay, so this is standard form. It's very easy to see transformations in standard form. Shift right 3, up 1. Let me show you that exact same problem, but in a way that it would make it very hard to see the transformations. If you took x minus 3 squared and you FOILed it out, it would be x squared minus 6x plus 9, and you'd have a plus 1. that and that are the exact same thing. There's no difference. In fact, I can graph each one of them and show you they look identical. Let's type in x minus 3 squared plus 1 and type in x squared minus 6x plus 10. Oh, okay. X minus 3 squared plus 1, x squared minus 6x. Okay, I have them both typed in. Let's do zoom 6. And if I did out the math correctly, they should graph exactly right over each other. So there's the first one. And then there's the second one. So they are exactly the same thing. This one is very hard to tell that you've translated 1 unit up and 3 units right. It doesn't even have a 1 or a 3 in it. It has a 6 and a 10. So if you were given something like this, you would have to figure out how to work backwards to turn it into that, to figure out the transformations. Okay, so in this class, that's not something that we look at. Okay, so I'm always going to give you your problems in standard form. Okay. But I'm just letting you know that might not be how it always is, like if you had to do this kind of thing in a different class. Any questions on that? Okay. So to fix something that's not in standard form, we have to complete the square. But again, it's not something that we're focused on doing right now. So we're not doing that right-hand side. All right, so the last thing we're going to look at is when you draw a parabola, I want to figure out how many different cases there are for what we call zeros. Zeros are where the graph crosses the x-axis. Okay, that's a 0. When I draw a parabola, how many times could it cross the x-axis? There's different cases. But what's one case?
Usually twice.
It could be twice. You know, if you had something like that, or you flipped it over. So there's twice. What would be another case besides twice?
Once.
Yeah, it could be once if it just kind of comes down, touches it, and goes back up. So that would be once. What would be a third case? Besides crossing twice or just crossing once? Yeah?
It doesn't.
Doesn't cross at all. You know. So that graph never crosses the x-axis. There's a quick way to figure out which one of these 3 cases you have. And that's what I'm going to show you. So for quadratics, it either crosses the x-axis 0, once, or twice. Where it crosses the x-axis, those are called the zeros. And the reason they're called the zeros is because if you know where it crosses the x-axis and you plug that number in, you'll get an answer of 0. I don't want to make up a quadratic, but if I make up something linear, just looking at the right-hand side, can anybody tell me what number you would plug in for x and it would cause you to get an answer of 0? Yeah?
3.
3. 3 is the 0 of this equation. 3 is the 0. Unlike a quadratic, it's the only one because it's a line. Lines don't cross the axis more than once. All right, how do you quickly figure out with a quadratic how many times it crosses the x-axis? Well, you've got to do a calculation. And the calculation you need to do is right there. It's b squared minus 4ac. Now, if you don't remember where the a, the b, and the c are coming from, the a, the b, and the c are coming from right there. A is the number in front of x squared, b is in front of x, and c is what's at the end. Does anybody recognize that? B squared minus 4AC? It's part of something. We're not doing the whole thing, we're doing a part of it. Yeah.
It's the top of like the quadratic equation.
Yeah, it's what's under the square root in the quadratic formula. So if the part under the square root comes out less than 0, then that means your graph will never cross the x-axis, and you have no zeros. If the part under the square root comes out to 0, that means your graph will cross the x-axis one time, and you have 1 0. If the part under the radical comes out bigger than 0, that means it will cross the x-axis twice, and there are 2 zeros. So let me just make one up. Let's do f of x equals 3x squared minus 2x minus 4. I don't want to know the exact answer. I just want to know how many times it crosses the x-axis. Okay. What's A in this case? Yeah,
3.
3. How about B? Negative 2. And C? Negative 4. Let's see what B squared minus 4AC is. What's B squared? 4 minus 4 times, what's A? 3. And what's C? Negative 4. Okay. So we have 4 minus, what's 4 times 3? 12. And 12 times negative 4? Negative 48. So we are subtracting negative 48, becomes addition. 4 plus 48 is 52. So based on the answer that we got, are we going to have no zeros, 1 0, or 2 zeros?
2 zeros.
Yep, this is going to have 2 zeros. We don't know where. All we know is there will be 2. And we can quickly confirm it just by typing it in. 3x squared minus 2x minus 4. Guarantee you, it will cross the x-axis twice. It has to. Okay, so that calculation is a quick way to figure out how many times it crosses the x-axis. All right, any questions on that? All right, so that is section 1.5, okay, quadratics and transformations. Okay, so the homework for tonight is those 9 questions on page 56. So it says 1, 7, 10, 18, 22, 28, 33, 40, and 44. All right, so we will take a look at those tomorrow. And then tomorrow, we're going to be doing one section again, just 1.6. And then Thursday, we'll finish up everything for the week, and then our test is on Friday. Okay, so on number 40, just make sure you use the problem that I'm giving you, which is a little different than the way they wrote it in the book, because we didn't talk about the way they wrote it in the book. But use that problem and then do what they're asking you to. In fact, I'll write down what the directions are. Just describe the transformations for number 40.